In our previous video, we discussed two things: the concept behind linear regression and creating a model based on our data observations that does a good job of predicting outputs for new input values. And we discussed the idea of an error measure for a model to see just how good a model is at modeling our data. What I'd like to actually focus on in this next video is the latter of those two, the error measure, and in this video we'll be looking at the residual sum of squares error measure. Again, I'd like to start out with a story to motivate what we're doing here. One thing that you might have encountered in your life if you've ever been at a carnival or a festival is that there will be booths there where the guesser may attempt to randomly guess your age or weight or perhaps your birth month. And of course, most people aren't going to be able to glance at you and get your age down to the number of years, months, days old that you might be. So they put a little bit of a buffer around how accurate the guesser needs to be. In this example, if the guesser is within 2 years of your age or 3 pounds of your weight, they're going to say, you didn't fool the guesser, you lost the game. However, if you did fool the guesser and you're significantly younger or older than they guessed, or heavier or lighter for that matter, you win a prize. Different carnivals might have different sets of rules, but one thing I've certainly seen is that it's also important by how much the guesser was off. There's already a buffer around how accurate the guesser needed to be, plus or minus 2 years or 3 pounds, and you may win a prize for fooling the guesser, but if the guesser was only off by 4 pounds in guessing your weight, you might only win a small prize. But if the guesser was really off, they guessed that you were 30 years old when you were really 50, you're both flattered and walking away with a very large prize because of how far off the guesser was in their assessment of your age or weight. This idea is going to very much fit with the concept of the residual sum of squares error measure. So let's look at this residual sum of squares much more accurately and with some pictures and some formal mathematics involved. Let's imagine that we're looking at some observations, some data, and we have our input values and our output values. For our purposes, we're going to let capital N denote the number of input values that we have, and we'll denote the whole collection or set of input values by the letter X, and we'll enumerate those individual input values as X sub I, X sub 1, X sub 2, X sub 3, and so on. Now we're also going to have two different collections of output values. There are the actual output values. We're going to want to think of those as a set capital Y or little y sub I values. Those are the actual Y values that you're seeing in this chart, the actual output values for the input values X sub I. If we have a model F, we also have the hypothetical or predicted output value. If I have a particular input value X sub I right here, that predicted output value would be the y coordinate on this function, denoted by f of the input value, X sub I. So for each X sub I input value, we have the actual output value, denoted by y sub I, and the predicted output value, denoted by f of X sub I. So we've got our observations, the black values, and our predictions, the blue values. This corresponds in our previous example to something like your actual age versus the age guessed by the guesser, your actual weight, your weight guessed by the guesser. What makes sense and aligns with perhaps your previous mathematical experiences for how would we measure error, we would measure error as the distance that we can see in these pictures from the actual output value and the predicted output value. Now, because we don't actually care if the actual output value is lower or higher than the predicted output value, we wouldn't ever want to think about there being a negative error. Whatever that distance between the actual output value and the predicted output value is, we would want that to be a positive number. We would represent all these little individual differences between what is observed and what is predicted by the absolute value of the difference between the predicted output value and the actual output value. So this quantity that we have written down and represented by this expression right here is for any one of these specific input values, the distance that we see right here. In order to get the total error of the model, the overall actual error, we would want to take a sum of all of the individual errors, and that accrued total value would be the actual error given by our model. However, there's a technicality in what was previously described that makes it a little bit hard to work with mathematically, and that's those absolute value signs. If you've done any amount of calculus before, you'll know that the absolute value function has some points where it isn't differentiable, and it's very hard to deal with those absolute value signs. And so what we're going to do instead is trade out the absolute value of the difference between f of x sub I and y sub I with the square of that difference. The reason that we're doing this is the absolute value signs were in place in order to make the error always be a positive thing. The square will accomplish that also. Squaring also preserves things. If I'm a value over here and I have a very small distance between the actual observation and the predicted outcome, small things, when they're squared, stay relatively small. On the other hand, if I have an observation down here very different from the value predicted by our model, that difference will be large, and the square of that difference will be large. So adding this square here gets rid of a handful of mathematical complications. It keeps small things small and large things large, and it makes sure that each individual error we're looking at is always a positive value. So instead of the model that makes a lot of intuitive sense for us in measuring the actual error, we're going to use this proxy, and this proxy, this sum of all of these individual errors, is going to be our residual sum of squares error model.